Okay, so let's see how we can solve this problem. It's the plucked string model, so something that you've actually already worked on. Uh, it's very similar to the vibrating string that you have solved during the lab. So let's have a look at that. So we've got this equation. So that's just second derivative in time is equal to v square second derivative in the x direction. We assume that x is between 0 and 1. So we've got something like 0, 1 for the x variable. So the string is held at both ends. Okay, so u is showing you the displacement of the string, so it's going to be held at both ends, so it's just going to be 0 at both ends, and we have an initial, so that was this one, the boundary condition, and we have the initial condition, this one, which tells you that the initial condition is going to be, you've got x between 0 and 1/2, something like this, and 1 minus x between 1/2 and 1. Okay, so this is my initial condition. So you can imagine that this is the guitar string, and you're just pinching it. All right, so plucking it. So use the Fourier method, so separation of variables. So let's write what we have. So this is really something you have to be able to redo. And the aim of the labs were really getting you to understand completely the method. All right, so we write, so Fourier, separation of variables, Fourier method. Okay, so let's write this. So we write that u is a function of x and t, and we're going to write that it has two separate parts. Well, a function of x times a function of t. Okay, so what does it mean for our equation? So the d2 square u over dt square is just going to be x times t second of t, and similarly we've got very similar stuff for the x part. So we have something like my equation is rewritten as t second of t times x of t is equal to v square times x second of x times t of t. Okay, and we're going to use the same ideas, meaning that we're going to put all the t's on one side. Let's put the v square with it. It doesn't matter if you put it on the other side, but let's do it this way. It's more, I would say, more common. But of course, if you use the v square on the other side, that's fine too. You will get some consistent results, right? Okay, so the idea here is, I guess you've understood that. We've got a function of t on one side, a function of x on the other side. They should be equal for any x between 0, 1, any t greater than 0. So the only way that this is going to coincide for all values is that this is always equal to some constant. Okay, and let's denote lambda the constant. Assuming lambda is positive, we're going to see, well, you may find that this choice of minus lambda with a positive lambda is a bit arbitrary, but actually if you do the contrary, if you choose plus lambda with a positive lambda, you could still go one step further, but then you wouldn't be able to adapt to the initial conditions. Okay, why? Simply because when you are solving those two equations, so I've got my x equation, x second is equal to minus lambda x on one side, and I've got my other equations, t second is equal to minus lambda v square t on the other side. You know that you know how to solve these equations. You write the characteristic equation corresponding to that. You've got so R2 is equal to minus lambda, R2 is equal to minus lambda v square, and so that means you have two pure imaginary roots, plus and minus I square root of lambda plus and minus I square root of lambda, well, times v, absolute value of v, and you know that this will lead to some solutions in cosines and sines. Okay, so x of x is going to be some constant square root of lambda times x plus some constant square root sinus square root of lambda times x, and same thing for the t stuff. Okay, so let's just ponder 1 second. Why would I want something like this for my x and not something like exponential of lambda x plus exponential minus lambda x? Because eventually I will have to set, for t is equal to 0, I will have to have this. Okay, I want that my x function is equal to some something that can't be expressed. Okay, this initial condition, I will never be able to express that using combination of exponentials. There is no exponential expansion, but there are some cosines and sines expansion. These are the Fourier expansions. Okay, so this is why I need to have my imaginary roots in order to have an expression using cosines and sines, because eventually I'm going to use that to create a Fourier expansion and express my initial condition. Okay, otherwise I would never be able to fit my initial conditions if I had only exponentials. Right, so on one side I've got this x expression, on the other side I've got very similar things for the t expression. So let's call that c cosine v square root of lambda t plus d sine square root of lambda t. Okay, so these are my two functions. Let's now apply all my boundary and the initial conditions one by one. Usually I will try to give them in the exact order that makes it the simpler to use. Okay, so the first initial condition that I've got is concerning u of 0t, so when x is equal to 0 and t is non-zero, I should get 0. So let's see what it means. U of 0t, that's my first boundary condition, is equal to 0. That means that x of 0 times t of t is equal to 0. That means x of 0 is equal to a, because cosine of 0 is 1 and sine of 0 is 0, times t of t. And t of t has well, either it's 0 always and then your function is always 0 and it won't be able to coincide with the initial condition. Either t of t is different from 0 and then it implies that a has to be equal to 0. Okay, so we got rid of that part. Next in boundary condition, second one, u of 1t is equal to 0. Okay, so let's do that. U of 1t is equal to 0. That's x of 1, t of t, right? So that's going to be, so we had a equal to 0, b sinus of square root of lambda times t of t is equal to 0. Okay, so here, you know, if I put b is equal to 0, I will again would have a completely constantly equal to 0 function, which would never fit any of my any non-zero initial conditions. So that's not going to be a correct choice. We should put sinus of square root of lambda equal to 0, so put square root of lambda is equal to n pi, okay? And that works for all values of n. Okay, so that's it. So what does my solution look like? Obviously, it's going to depend on n. What do I get? I get that un of xt will be some bn sinus of square root of n pi times x times cn, okay, because I'm going to choose square root of lambda is equal to n pi. So I could say that all my constants can depend on n. So cn cosine of vn pi t plus dn sinus of vn pi t. Right. So now we use the superposition principle. Change that, superposition principle. What is that? It's just the fact that you have a linear equation. So if you sum and homogeneous, even if you sum the corresponding equation corresponding to different solutions, it's just going to still be a solution. So that tells you that u of xt, which is going to be the sum for all n in n of un of xt, that's still going to be a solution. And that's really fine because that's a solution of the equation that satisfies the two boundary conditions. Okay, if all the UNs are equal to 0 at both ends in 0 and 1, then the sum is still going to be 0 in 0 and 1. And we want now to use the last condition, all right? The last condition being no, the anti-last condition. Sorry. So the one concerning the initial condition, right? So what do we have left to find? You know that if I expand this sum, I will have Bn times Cn, okay, and Bn times Dn. So actually, I just have those two products to find. All right, so let's write these as Cn prime and Dn prime. Okay, so I've got sinus n pi x times Cn prime cosine n pi vt. Let's write it this in that order. It's easier to write. Plus d prime n sinus n pi vt. Okay, so that's it. Now I have to fit my initial condition. I know that for t is equal to 0, I know that u of xt is equal to my plucked stuff function, so to my triangle function, to this one. So I have that phi of x is equal to, so when t is equal to 0, I've just got the Cn prime. Sum of the Cn prime sinus n pi x. Okay, from for n in n. Well, in n star, because anyway, when n is equal to 0, that's just 0. Okay, and so what do we identify here? We just say, well, this looks like this is the Fourier sine series of phi. We have proved in the chapter about Fourier series that a trigonometric series or a Fourier series expansion was unique. Okay, so this is how I would write the Fourier sine series expansion of phi, and that's so I know that those Cn prime are going to be the corresponding Fourier coefficients. Okay, so that means that if I've got a sine expansion, what does it mean? My function, I remind you, was this one. If I've got my sine expansion, that's 0. That's 1. It means that I have extended my function by odd parity. So something like this, minus 1, 0. So in order to have an odd function, in order to have a sine expansion, and then I've got periodization in order to write the sinus series. Okay, you remember that? So what does it mean in the end? It just means that the Cn prime are given by, so I just apply the formula, 1 over half a period. My period is obviously equal to 2, so half a period is just 1. Integral between -1 and 1 of my phi function times the sinus of n pi x, okay, dx. And as we've got a product of two odd functions, that's going to be an even function. So you know well that this simplification is always happening in the Fourier series context. In that partial differential equation context. So I've got that this is going to be equal to 2 times the integral between 0 and 1 So 1 over 1 was 1, but then instead of calculating the whole integral between -1 and 1, I'm just saying that as the inner function is even, that's just going to be 2 times the integral between 0 and 1 of that same stuff, n pi x dx, okay, which in turn is equal to, well, I have to use the expression of my function, so between 0 and 1 over 2, that's just going to be x sinus n pi x dx plus 2 times the integral between 1 over 2 and 1 minus x sinus n pi x dx. Okay, both are going to be treated by IBP. First one, well, u of x is x, so that u prime is 1, v prime is sinus n pi x, v is 1 over n pi cos n pi x, well, with a minus sign. And on that side, I've got this one IBP. U is 1 minus x, u prime is equal to -1, v prime is sinus n pi x, v is minus 1 over n pi cos n pi x. So now let's plug this IBP 2 times. So x over n pi cos n pi x between 0, 1 over 2. Minus from the v gives me a plus, so plus 2, the 2 that was factored here. 2 integral between 0 and 1 over 2 of 1 over n pi cos n pi x. Okay, that's for the first one. Second one is just going to be 2 times. So 1 minus x. I've got a minus sign. I probably had a minus sign previously too, sorry. Here I had a minus sign. So here 1 over n pi cos n pi x between 1 over 2 and 1. And minus, that's still giving me a minus. I've got 3 minuses. 2 times over n pi integral between 1 over 2 and 1 cos n pi x dx. Okay, so what do I obtain? Right, so I'm going to get here I get in 0 it's just going to be 0, and in 1 over 2 I've got the cosine of n pi over 2. All right, so I get what's left of this. 2 times minus 1 over 2 over n pi cosine n pi over 2. That's a bit too thick, so let me just rewrite this. Minus 1 over n pi cosine n pi over 2. Okay, value in 0 is just 0 because I've got the x as a factor. Then I've got 2. I can find the primitive of this, so 1 over n square pi square sinus n pi x between 0 and 1 over 2. This one, in 1, it's just going to be 0. In 1 over 2, so the minus is cancelling. So I get 1 over 2 times 2, so 1 over n pi cos n pi x, n pi over 2, sorry. So the good news is that it's going to cancel with the previous one. Okay. All right, and I've got minus 2 over n square pi square, the sinus of n pi x between 1 over 2 and 1. Okay, all right, so what do we get? Thing is that we're going to get, so I've already said that these cosines were cancelling. This one I get, so in 1 over 2, that's going to be fine. In 0, it's going to be 0. So I get 2 over n square pi square sinus n pi over 2. Okay, and here I've got, so in 1 it's just going to be 0 because that's in the sinus of n times pi, and in 1 over 2 it's just going to be non-zero, and so that makes a plus 2n squared pi squared sinus n pi over 2. Okay, so this is going to be giving you 4 times over n squared pi squared the sinus of n pi over 2. Just to be clear, so, and that's the Fourier series, the sine expansion of this one, okay, of this one, right? So it's going to be equal everywhere on this one, and in particular, what was interesting us here was just between 0 and 1, right? So that's also Fourier series exercise. That's very interesting exercises. Of course, you understand that. Okay, just to be clear, that's going to be 0 if n is even, if n is even, okay, and that's just going to be plus or minus 1, plus or minus 1 if n is 1 plus 4 times something, or 1 or 3 plus 4 times something. Okay, so that's it. So what have we found? So we know that this is actually the Cn prime. We don't need to plug that maybe in our expression for un. What was that? Okay, so maybe let me just see where we are here. So we have found this. We still have to find that. In order to find that, we're just going to use, well, the last condition that we have. The last condition that we have is this one: the derivative according to t of my function when t is equal to 0 has to be equal to 0. So let's work on that. So my fourth initial well, boundary condition, well, initial condition, tells me that I should differentiate that with respect to t. Okay, so sorry, my last expression, this one, u of xt, this is the one. So we should differentiate that with respect to t. So du over dt xt is going to be given, and then I will have that my that I take t is equal to 0, so that the cosine that I have here, which is going to become a sine when we differentiate that, it's just going to be 0. So I will have just this one left, right? So what do we have? We will have the sum. Okay, we have the sinus of n pi x. The cosine, so let's take that for t is equal to 0. The cosine is going just to be equal, well, that has been differentiated into a sine, it's just going to be 0. And then I've got d prime n, I've got n pi that comes from the differentiation, and I also have the v. Okay, and I have, what else do I have? And then I will have some cosine of something 0, so that would be 1. Okay, what does this tell me? This tells me that this is equal to 0. So how could I consider that? I could consider that as the Fourier sine expansion. That's a Fourier sine expansion of the 0 function. Okay, my sum of sinuses is equal to 0 always for all x's between 0 and 1. Okay, so that's my is an equal to 0 function. So that just tells me that I have that t prime n is equal to 0 for all n. Okay, and finally, I can write that my solution is given by u of xt is my sum of the sinus n pi x, so the d prime is 0, and I just have got my c prime n, which was 4 over n square pi square sinus n pi over 2 times my cosine pi n pi v t. Okay, and this is it. This is the complete solution of that plug string equation that we obtained by the Fourier method.